Yeah, everyone. Good evening from Sri Lanka and good morning to the USA. Astronomy. It's pleasure to present Astro Week 2026 organized under the Astrobiology and Paleontology Certifications Program. The topic of the today lecture is Beauty Filters of Mars, how remote sensing allow us to study the red planet. For this lecture, we are honored to welcome our distinguished guest speaker, Rina Faber. Rina is a PhD candidate in astrophysics. So, as a chief executive officer at the LunarCo, a Luna focused company, develop next generation mission design, a platform integrate with the Web3 technology. Her expertise span planetary science, space medicine, and mission a critical instrumentation. She had contributed to the several major international space programs, including ExoMars and Luna-26. Her doctoral research focused on mineralogy of the Mars surface deposits using the hyperspectral remote sensing, offering new insights into the geological evolutions of the Mars and potentials for the future exploration. In the parallel, she led a research at the Federal Research and a Clinical Center of the Space Medicine, where she developed astronaut health risk management strategies and lunar environmental simulation system, a strong advocacy for the science educations, including the Faber is a founder of the Women Space Academy. The current research and development activities, including the astronaut health optimizations and lunar dust mitigations and the advanced remote sensing studies, both Mars and Moons are going to be truly tremendous. We are delighted to have a Faber with us and looking forward to an inspiring and insightful lecture today. With that being said, I would like to invite this young, talented scientist favor to address Equestrian International Platform. Now it's your time, Rina. You can get started.
Hi everyone, good evening and good morning. I thank you for introduction.
Yeah.
I will start sharing my screen. So tonight I want to show you Mars, like I hope you probably never seen it before, and maybe never imagined it could look like that. And I assume asking whether you love space or geology. Uh, it would be um, it would be great that if we could immerse ourselves in this. So let's start with simple things because I don't know the main auditory. Maybe it will be in different levels. So I hope we will adjust to that later. So let's start with the basics and with the analogy that everyone will understand. So what do filters have to do with Mars? I think this slide make it pretty clear which beauty filters I'm referring to. And I I could ask you to raise your hand, but let's not do that because I don't see anything from my presentation. So um, just ask yourself a question: how did it feel like to look at yourself through that mask? At the very least, it was probably amusing and unusual, right? So it's been about 7 years since Snapchat introduced the first filter, and during this time, many people around the world they have developed a real dependency on them. If we know that. So much like with many other new technologies, and here's the thing: we've been using beauty filters on the universe for decades, and right now I'm going to show you exactly how. So let's start with just different analogy, but for astronomy. Let's return to space. And how did people first fall in love with cosmos and start dreaming of space travel? Uh, first, they gathered at breathtaking views in the nature for like of Milky Way, for example, like this one on the left. And this is what you actually see with your naked eye. And and then we started seeing images like the one on the right, which we save to our phones and set as well wallpapers. But let's pause here to understand the difference between these two images. The image on the right is also a real image of the Milky Way, but it's what a camera can capture. Device that can accumulate light from an object over long exposure time, and in this case it's 50-second exposure. If you're trying to find your dropped keys, for example, in the dark, no matter how long you stare in the darkness, they won't light up in front of you. So this is our the next level, the first filter, long exposure photography. It reveals what our eyes cannot see. And let's look at this slide. So let's dive into 90s. Who loves 90s? So when the world saw the first photographs from the Hubble Space Telescope, I think you all know these pictures. A new era began. We were no longer just flying into space. We were photographing space and watching it from our couches. So this cosmic fever continues to this day. We dream about conquering the cosmos. Imagine how one day flying on our own starship, we'll see such fantastic landscapes through the windows. And this is a cluster of gas and dust in the Eagle Nebula. It's around 6.5 thousand light years from Earth. And these are the famous pillars of creation, so-called pillars of creation. And on the left, you see Hubble's image from 2014 and taken in visible light. On the right is the same region captured by James Webb Space Telescope in 2022 using near infrared and mid infrared wavelengths. We will talk about this later. So notice how, and let's pause it here because I mentioned about 90s. So this picture was taken previously in 90s, and then it was recreated with new technologies. So it's new data from 2014. So notice how different they look. That's because Webb can see through the dust that blocks visible light, and it's revealing the young stars forming inside these pillars, and same object, different filters, so a complete different view of reality. And almost a reality. Let's through this. We understand this are enormous distance are and interstellar travel probably won't become reality on our lifetime. So we still want to dream, don't we? So if we want to go to Bali, for example, we can at least go to I maybe Philippines, right? So if we can travel to the Eagle Nebula, maybe we can look toward Mars. And we have Elon Musk, and he is winking at us and working on this really hard. So to sweeten the bitter of not the small possibility of space travel today, so Sweden will be like it's almost a reality what we are looking in this picture. So this is the thumb of a pillar of creation, and like clusters of interstellar gas and dust. And this is about 61 quadrillion kilometers in the picture. Even at the speed of light, it would take us 6.5 thousand light years to go there. So Mars, on the other hand, is only about 20 light minutes away, so it's closer to us. And that's our local neighborhood, practically next door in space terms. So what we look in here, if we will go near this nebula and we will not also see this picture with our own eyes, it will like take us 8 seconds exposure to gather this light into this picture. So it would be, in reality, it would be dimmer than this. So, and let's go to everyday astrophotography truth. So all the photos we are accepting from space, they weren't captured by a human eye, so they taken by cameras for practical and scientific purpose, of course. And this we also look on this 8-hour exposure picture here, and the colors are real, but they are as all astronomical images, they are fundamentally black and white. And astronomers just not just the artist making money while actually shooting a grayscale. So let's dive into that and let me explain how this actually works. So that's will be our journey today. This is our roadmap. And let's go to this road today. So I will talk about spectrum in general, then about Mars remote sensing, and then I will show you some Mars maps. We will talk about a little about Mars mineralogy and the remote sensing itself. So that will be our journey today. And let's start with the riddle. You could read it here, and I will not read this out loud. So that's like 5 points here, and what is it? So, and answer is electromagnetic radiation. And light, heat, and radio waves, X-rays, they are all forms of electromagnetic radiation, and understanding how it works is the key of understanding how we see Mars and the entire universe. So let's dive into this diagram. I think you maybe already know everything that is here on this picture. So electromagnetic waves, they are similar to ocean waves. So they carry energy, and they carry disturbance created by vibrating charged particles that process electrical and magnetic properties. But unlike ocean waves, which require water and medium to propagate, electromagnetic waves travel through space vacuum at a constant speed of light. And the electromagnetic spectrum spans from radio waves to gamma rays, and radio waves are could be like kilometers in length, and gamma rays could be with wavelengths smaller than atom. So somewhere in the middle is this tiny visible line of visible light. So the only part our eye can detect and see and perceive. So this is crucial. Our eyes can only see tiny fraction of reality, and everything else is different, is invisible to us, but that's all there, carrying information about our universe. And when we detect it, we can research what we could know about. So how we perceive color, let's start with that. And every objects have color because wavelengths interact with the molecules they made of, the objects made of. So some energy carried by wave is absorbed by molecules and some is reflected. This apple appears red because when light interacts with red skin containing cyanidin, it's a pigment. Certain wavelengths are absorbed while red wavelengths are reflected back to everywhere, and also the detectors, so our eyes. And our perception of color is really just our brain's interpretation of which wavelengths of visible light are bouncing off an object. So that's it. And when we look at a rock, we see in the entire visible portion of electromagnetic spectrum. That's the part of spectrum human eye respond to. So when we all we have all seen that when light passes through a prism, it splits into various colors that make up the visible spectrum. So each of these colors corresponds to a specific wavelength of light. And we here today I will talk about wavelengths in nanometers. And 1 nanometer equals on 1 billionth of a meter. So human eye is sensitive to light in the range of about 380 to 750 nanometers. And what about infrared light? So the invisible heat. So infrared cannot be seen, but it can be felt, for example, by humans. So it could be felt as heat. Every object, hot or cold, emits infrared radiation, and special thermal imaging cameras uses colors to show us whether something is warm or cold. And some objects are hot enough to produce visible light, like stars or molten lava, for example. But things that are too cold to see with the naked eye that can still emit in the infrared range, like your body or a cup of coffee. So IR light has incredibly practical application. Longer IR infrared IR waves, they can cook your dinner, for example. So microwave ovens use related technology. Shorter IR waves are used, for example, in TV remote controls and every other remote controls. And firefighter, for example, they use IR cameras to see through smoke and find people trapped in the fire. So for astronomy, infrared wavelengths can see through large amount of gas and dust, lighting the view on what lies beyond. So, for example, Spitzer Space Telescope. So objects like exoplanets on or the Milky Way by detecting their infrared glow from the heat they radiate. So let's go to what is broadband filtering. While your standard camera makes phone camera makes images using entire visible part of the spectrum, most astronomical instruments they image objects that using only a small portion of the wavelength range. So cutting out everything except a small part of wavelength range in the job of the filter. So look at this three spectra, and these objects have very similar in the color. So we have like here red, green, and blue, and when we just combine these three images, we will have this whole picture of color image. And this how the RGB model work. So these three colors, this is how our computer screen, for example, your phone, create colors. So by combining different intensities of these three primary colors, we can create the illusion of millions of different colors, but this is just for the visible portion of the spectrum. And in astronomy and planetary science, we expect this, extend this concept, and we can assign any three wavelengths to red, green, and blue channels, including wavelengths our eyes cannot perceive. So this creates what we call false color or pseudo-color images. They're not fake. They're revealing real information that our eyes simply cannot perceive directly. So that's how it's work. So there we we take three broad filtering things. We just shift this into from infrared to visible spectra, and in false color images we're doing this with wavelengths that we cannot see. We measure how bright an object is at different wavelengths. Then we choose specific wavelengths to display in artificial colors to highlight intensities of variation. And this is somehow abstract, but we use two things we can see, color and geological context, to observe things that we cannot see directly. That's mineral composition, and after careful analysis and interpretation, long vanished environments and geological changes that occurred over vast spans of time can be perceived. So that's James Webb pictures that you already seen, for example. I think you see them. They are like already several years old. So here is a near come of James Webb Telescope, and this telescope, this camera also have the same technology, and it's composite images from three filters for like we see here. It's a red, yellow, green, and cyan, and the planet alignment appears slightly due to Jupiter's rotation between exposures. So notice how different this looks from the Jupiter we used to see. So here, like a great red spot appears bright because of the specific wavelengths. And here, Saturn. The interesting thing about this particular picture that the rings are blindly bright here, while Saturn itself appear relatively dim. This is because at the infrared wavelengths, observed by NIRCam. Methane gas absorbs sunlight in the planet's atmosphere. So what with the icy rings? They reflect light at these wavelengths, and the three of Saturn's moons appear. You can see them as points of light of the left side of the image. So same planet, different filter, completely different perspective. And this is Uranus. So that's also we see its rings that we are not see on the classic images. Neptune. And let's go to some scientific terms. That will be one for today, is albedo. So it's a crucial concept of understanding planetary surfaces, and albedo is a characteristic of the reflectivity of a surface. So it's ratio of the radiation flux scattered by the surface in all directions to the flux incident on it. And so when we look at the scale, when we look at here is the scale for from white to black. So this is the different ratio. And let's go here. And what we see here. So when we measure albedo while also tracking the specific wavelengths of light, we create what's called a reflectance spectrum. There is different types of spectrum. So on the x-axis, we plot wavelengths of light. On the y-axis, we plot albedo at the wavelengths. Think of it like a barcode for materials. Each mineral, each rock type has unique spectral fingerprints. And for example, this is a real spectre of a white sheet of paper, because it reflects about 60% of light at all visible wavelengths. And that's why it appears white. A black sheet of paper has only 7% reflectance, and a gray sheet somewhere in the between, like 0.05. So let's look at this. And here we see the difference, because it's how it look like for red objects to appear. So this is a spectrum for the red object. And rocks are composed of sets of minerals, and these minerals are made of specific elements arranged in crucial, crystal structures. When light reflects from a rock, the various crystals absorb and reflect different wavelengths, and by looking at the reflectance spectrum, we can get an idea of the minerals the rocket is made of. And this is incredibly powerful for planetary astronomy. We can determine rock composition by looking at reflected light without even landing on the surface. And this is called remote sensing. So, for example, it's spectra from various basalt samples here. And notice the visible part of the spectrum is just a small portion of the graphed range. And you can see that a lot of interesting things happen beyond what our eyes cannot detect. and particularly in the infrared. And remember, you cannot see beyond the visible part of the spectrum. So if I ask you what's something look like, don't consider the infrared or ultraviolet. You won't see anything there, but our instrument can see there, and that's where we find the almost diagnostic information about mineral composition. And so let's look here. It's also the continuation of the spectrum, and this is three different type of basalt, and we see that we have really really unique from one perspective, and really like same images, same lines on the different type of basalt. And if we go further into the spectrum, we see the difference in the spectra, and that's how it allows us to understand the difference between these three types. So let's go to remote sensing. This is a diagram that show us how a human eye, hyperspectral camera, and what is hyperspectral images. So on the left, we see the fish. That's how natural color image of the fish. And hyperspectral camera is taken all these different channels of wavelengths, and then it's like stock it into a pile that we called hyperspectral image. And oh, okay, so it's let's here. Okay, oh, it's working. So this is example of hyperspectral imaging. That's it's a lesson learned from NASA's hyperspectral data work presented at SAT Summit in 2022. So here we could see the difference between three different ranges that we could operate in. So it could be visible light, it's a RGB model, like we already talked. And the second one is multispectral. And the third one is hyperspectral. Let's look into this, and I will go back to the previous image. So in RGB model, we have only 3 channel. In multispectral, we could have from 4 to 7 channels, for example. And in hyperspectral, we have so many variety of the filter that we could see. So it's hyperspectral imaging takes remote sensing to the extreme. Instead of a few wavelength bands, we capture hundreds of narrow spectral bands for each pixel. So this creates what we call image cube, and we will back to that later. So here is a really good infographic that are showing you the difference between these 3 regimes, and you could spot the difference in hyperspectral mode when you have data through all of the wavelengths in nanometers here. And for multispectral, there is no data, and so on. Okay, so yeah, this is the picture how we perceive the information from our Earth in space. So Earth observation. Oh, okay. I double the slides. Yeah. Okay. So what we're looking at here. This is the same as Earth's observation, but for Mars, and this Mars Reconnaissance Orbiter. And that's like complete chemical laboratory analyzing every point in your image simultaneously, and that's the insights of this orbiter. We have different instruments, and for example, it has a context camera or CTX. It gives us a global map of Mars. CTX camera brought the Mars Reconnaissance Orbiter. It has been imaging Mars since 2006, and the scientists have stitched together. Okay, here, stitched together over 51,000 individual images into this stunning mosaic. You can go to this QR code and look yourself into this. So resolution allows us to see features as small as 6 meters across. That's the size of a school bus, for example. So grayscale image shows the topography and geology of Mars in visible light, but we learned that there is so much more to see. And this is the most, I think this the most recent Mars map that was made with observation of Emirate Mars mission, HOPE probe. That's the real map of Mars. So we slightly go for Mars maps. And this is the real color of Mars. And this is black and white Mars. And it's a 3D globe that you could see all the features. And this is all is a flat image of 51,000 individual plates. And that's how what is this hyperspectral cube. So that's how we transform raw spectral data into mineral maps. So it's a particular feature of this prism is a camera that takes hyperspectral images. And what we have in one cube of data, we have 6 billion spectra. So it's an image cube, mineral map, and Mars map overlay. And each spectrum is compared against the library of known mineral spectrum measured in laboratories on Earth. So we every time we compare with Earth samples, because we don't have samples from Mars yet. So when we find and match, we can identify what minerals are present in the location on Mars. So process is computationally intensive. For a single tile, optimization can take anywhere from 5 hours in exceptional cases to more than a day. And creating a map of the entire planet takes about a month on a computer cluster. So here we can see the first artificial, let's say that map, dust map. So we're looking here on the dust on the Mars. This is a global map for thermal emission spectrometer, or TESS, that was on the orbit of Mars in 2002. And TESS was a broad Mars global surveyor, which operated from 96 to 2006. It measured thermal infrared radiation from the Martian surface. And red here indicates bright dusty regions, and blue indicates darker rock-dominated areas on Mars. And this was how we identified landing sites for Mars exploration rovers. Spirit and Opportunity were targeted specifically to land in areas where TESS has detected interesting mineral signatures, particularly hematite. And it's a iron oxide mineral that forms in the presence of water. And this is next generation. Is Omega. Uh, it's a ExoMars Express camera, uh, Observatory pour la Mineralogy. Eh, and this was a broad ESA Mars Express spacecraft. It was observing Mars since 2003, so it's 10 years, providing the first global uh, perspective on Martian mineralogy from orbit. And in 2004, Omega made a groundbreaking discovery. The Martian South Polar Cap is two layered. It was the discovery that it was two layered, and the spectra showed signatures of both water and ice and the carbon dioxide ice simultaneously. So this was one of the first direct proofs that beneath the dry ice lies water ice, and it was a crucial finding for understanding Mars water history. So here we also looking at the dust, and remember this 2000s, 2010s, and this is the same map for the dust, but it have different false color range. So here the rainbow, and here this two blue and red. So, but it's the same dust map. So CRISM is a compact reconnaissance imaging spectrometers for Mars. It's arrived at Mars in 2006. And it carries one of the most advanced instrument at the time that suits either sent to orbit another planet. So this nearly global map consists of approximately, as I already said, 50,000 mapping strips. They mosaicked into 1,764 tiles. So we are looking here at 5.6 gigapixel image in 72 colors. That's revealing the, not here particularly, but in the strips, revealing the mineral composition of Martian surface in unpredicted details. So these are the yellow square that I zoom in. So as I already said to you, the different colors. Here is also dust, and we have these regions that are where we cannot have data. It's not like we didn't capture this with camera. We captured, but it couldn't be combined with the different strips, so it's better not to put it on all mosaic. So we see here Nili Fossea region, one of the most mineralogically diverse areas on Mars, and there's a place where the Perseverance rover is currently exploring. And the map shows familiar large-scale patterns of surface brightness, so largely determined by the distribution of bright red dust contains iron oxide, And the darker dust-free areas consist of broken impact rock and wind-blown sand. Is in a blue color here. Okay, what we have. Okay, so that's in comparison the different of TESS, Omega, and CRISM. You can see the spatial resolution here. It's a 3 kilometer and that TESS have on 1 pixel. On 1 pixel is a 3 kilometer of information. So on Omega, it was 1.5 kilometer per pixel, and in CRISM we have like 235 meter per pixel. So that's 13-fold improvement in just 20 years. So with CRISM, it can distinguish features the size of a few city blocks combined with high-rise camera images as a high-resolution camera that have resolution like 30 centimeters per pixel. And we can now study Mars with nearly the same detail we use on Earth. So what I think, oh, okay, this we have this image here. So this is about resolution. You see these details that we can see here, and we obviously cannot see it here. Okay, let me back to, let's wait. So I just want to say that each pixel in CRISM, it contains a complete spectrum, not just 3 color channels like a regular photo, but it's 544 wavelengths from visible through infrared. And a high spectral resolution allows identification of iron-bearing minerals like olivine, pyroxene, or iron oxides like hematite, or hydrated minerals like phyllosilicates, clays, sulfates, or carbonites. So the wavelength sensitivity from 0.4 to 4 micrometers allow us to identify rock-forming minerals and, crucially, minerals that form in the presence of water. Okay, sorry, it's in Russian. So what we can see here, this old square that I showed you, but in the different filters. So top left is we have these false colors. When we synthesized color that composed showing us iron mineralogy different, for example. So red is iron oxide. Okay, yeah. Let's have a moment to breathe and go into geology. So let's look here how it's all work in tiles. So for example, here we have red pixel, okay, blue and cyan. So 3 colors that are assigned to our RGB model. We also see here spectrum, and here red is iron oxide, blue is iron bearing minerals like olivine, high calcium pyroxene, and the green is low calcium pyroxene. So bottom left is like water altered phyllosilicate clays, rich in iron and magnesium, plus some carbonates, and warmer colors here, they indicate stronger feature. That's how we could understand this difference. So in the bottom, when we have this three range, like red, green, and blue. So red is olivine, green low calcium pyroxene, blue is high calcium pyroxene. So we distinguish this from our spectrum, and then combine it and have this full color image, but with geologic correct information. And let's look in practical cases. And that's the one of here. So Mars is geologically diverse world, and despite its reputation as a dead red planet, Mars preserves a record of ancient volcanic activity, impact events, and most importantly, water alteration. And minerals we detect tell us the story of conditions that existed billions of years ago when Mars was more alive and active. And we cannot have this on Earth, for example, because on Earth everything differs really quick. So here what we looking is CTX, but a high resolution image of a side of the crater. And this is, we could think about this is this minerals that it happens when you look at this and naturally you think about that there is a water interaction, and we see here water tracks. But if we look in the filter, we could see these mafic minerals. It's magnesium and iron rich minerals that form from cooling magma. And this is how we distinguish some the water presence, for example. So this image shows gullies on the edge of Gala crater, where the Curiosity rover is currently operating. So the area shows us nearly 150 kilometers. So olivine is one of the first minerals to crystallize from the cooling magma, and pyroxene is a common in volcanic rocks like basalt. So here we can look into impacted deposits, and on the right is the Earth sample of this. So it's impacted is rocks that have been melted and altered by meteorite impacts. And Mars MRO discovered deposits of impact glass in crater of Mars on Mars. And this type of glass forms from the intense heat of meteorite impacts. And the exciting thing about that, research has shown that impact glass can perceive evidence of past life here on Earth. And in 2014 study, researchers at Brown University found organic molecules and plant material buried in impact glass formed million of years ago in Argentina. So that's we are looking at. And scientists suggest that similar processes could have perceived things of signs of life on Mars, ancient life on Mars. So if life was present at that time of the impact, This opens a potential new strategy in the search of ancient Martian life, for example. So let's go to water on Mars. The most common nickname for Mars is red planet, and this is evokes image of inert desert world devoid of water and life. And this reminds us of endless sandy seas and the brownish yellow sky of thin atmosphere. So, but over 40 years ago, satellites images showing dried river channels and ancient craters, lake beds indicated that Mars was once warmer and water and more wetter and more dynamic than it's today. Sorry, and the question was how much water? What was the chemistry? How long did it persist? And most intriguingly, could it have supported life? So clays are obvious indicators. The bottom of any water body contains a clay, as well as carbonate salts and hydrate sulfates have water in their chemical composition. And hydrated silica, it contains water in the structure. And every time we detect these minerals, we detect an evidence of ancient water. And this slide is how it, so it's in 2018. Scientists analyzed Mars's radar data, observed, discovered what appears to be liquid water lake beneath the southern ice cap, about like 1,500 kilometer below the surface. And the water is extremely salty there, which keeps it from freezing despite temperature below zero. But here we are looking at trapped water, and this is on the left is a recreation of how Mars could look like 3 billion years ago. So subsurface ice survey shows approximately 5 million cubic kilometers of ice in the surface and up a permafrost layer. So if melted and spread evenly, this would create a global ocean in depths like 35 meters at minimum. So, but it's just a fraction of what motors one have ahead, and that we could see it on this particular slide. So let's summarize what we learned today. I will not read all this, but we talked about how we perceive colors, what is spectrum, what is hyperspectral imaging, slide. Really fast track on evolution on Mars exploration and applied value of remote sensing. And we conclude with that Mars has water, of course. And the beautiful Mars images we see are not lies, of course. They are translation of invisible light into colors we can see, revealing a world far more complex and fascinating than our eyes alone could ever show us. So I think that's all for today. Some some of beautiful pictures with filters of Mars. Let me end with this. This is Tess. Oh, so this is the first image that we have, and then it's a crazy. So here a QR code for all my project that are related not to Mars but space exploration.
Okay, sounds very interesting, and we have just already got through it with the many of planetary bodies, expected some of Mars, terrestrial land, including those splinters. That is really fascinating. And dear students, now we are opening for the Q&A sessions. If you have any further question, make sure to raise your hand. Otherwise, like you can just drop into the chat box. And I'm just coming to the chat box sooner. And before that, I have a few couple of questions to the Rina. So, like, why you are that much interested in having using some remote sensing and the filtering and to try to understanding Mars and why not Earth? Like we can just apply that same things to the understanding Earth, no? We have been just already done. Why you are fascinating about the Mars and including that remote sensing part?
Thank you for that question. I think, let me think. Um, you know, I didn't study remote sensing in my first. So the answer to your question is simple. That's how uh, that's really naturally emerged from my study process. So I started with astrophysics, and uh, the main tool that I used was photometrics, um, and then I just turned from stars to asteroids, and from asteroids I I went to all to Mars and Moon, and then at the end of my study journey, I I end up with remote sensing of Earth observation. So that's so I think it's historically just just how it went when you have things like you're fascinating about, like space exploration, you don't think of our home like the place that you want to study, because you already live, you see it with your own eyes, and it's not like it's not interesting, it's more fascinating, and the possibilities. Your question is really deep, in terms of that Earth observation data. It's emerged in recent 15 years. That's Earth observation data how we know it today, and it kept to evolutionize and differs, and it have more to say in the future with new technologies. But um, the difference between Earth observation and observation of different planets or even exoplanets is that all our planets and moons in our solar systems, they are kept in like in historical museum, so we could see everything that how it encapsulated in 3 or 5 billion years ago, and that's not how that's not possible on Earth, because everything is changing here with a span of 1,000 years, even smaller.
I see. Thank you very much, Rina, for answering that question. And also, like, I noticed that you have been just already enrolled in the space medicine sector. Can you just share in that your personal experience and how you feel that why you are that much interested about space medicine, and if it is any young scientist who interested about that field and what are the opportunities?
You know, I always want to fly to space myself, and I still have those plans for myself in the future. And what I do in space medicine, so I try to find my way into space, space engineering and space related topics of research. And what I'm what I'm focused in space medicine is it's a developing risk mitigation strategies to ensure the safety of future human space flight to the moon and beyond. So beside of Mars, I study the moon and also the mineralogy of the moon and how dust on the moon are formed, what's is the uh, toxic toxicity of the moon dust, and this how all of this could be related to risk mitigation but for the space exploration. So that's my way into space medicine, particularly.
That sounds very interesting. So right now I'm moving to the chat box and let's check, dear students, what are the questions that available. Okay, let's check starting from the Kavindu. My Unicode is not that much good. I have done some mistake, but anyway, like I'm go through with the Kavindu's questions. He have been just put it in single medium. Let's check what he just did. Yes, Kavindu. මම හිතන්නේ මම ඔයාලට ඒක සිංහලින්ම answer කරන්නම් කවින්දු. මේ ඔයා terahertz ගැන අහලා තියෙන්නේ. 1 terahertz එකක් කියන්නේ 10 බල 12ක් වගේ hertz. එතකොට අර ඒක 10 බල වලින් කියන එක තමයි terahertz වලින් කියලා තියෙන්නේ. Right? So then I'm moving to the second questions from the Arunan. Could there be chance to do spectral studies of the Mars and others? I mean, I think like he's asking about is there any link, websites or checking with that spectrums, images and the data?
Yes, of course. You could go to the simple way for that is to go to. There are many possibilities to study that. Also, you could go to CRISM site. You could type CRISM NASA, and you will be directed to here at the main site. Here, Mika filters. All information you can find here. Also, you could download some tools that you could use and have pictures like that. So I already showed you this. So that's all about Mars mineralogy.
Okay, sounds very interesting. I hope, Aaron, you got the answer. Then I'm moving to the next questions from the Teomini, Amano. And are the minerals formed on Mars due to the ancient volcanic eruptions? I feel like she's asking about.
Yes,
that.
also volcanic eruptions. Yeah, I don't think that I have anything to add here. So everything like we have here on Earth, but in the different time scale. So the evolution was not like on Earth. So we have like 3 different evolution tracks. We have Earth in the middle, as we know it. We have Venus, and we have Mars. So Venus and Mars, that's 2 different fate of our Earth in the future and in the history of formations. So that's really interesting into comparison and how that all formed in through all this billions of years.
I see. So, and there are some additional part of that questions from the terminate. She's asking like, are the false color related to the RGB modules?
Yes. So every false color is one of the color from R, G, and B. So red, green, and blue. Yeah, we can combine it and have different set of colors. For example, yellow and so on. And that's we assign them to different feature in other wavelengths bands.
See. Dear students, if you have any further questions, make sure to drop into the chat box. And like Rina, if the some young people who interested to join the like planetary geology or planetary explorations, like such a field, so what will be the your best advice to them?
Um, I think the one advice that I would love to give is that don't restrict to yourself that you cannot study something because of your background. So if you are in the different field and you want to study this, just go for that. And so don't stop yourself from doing that. Uh, and also you could do this as a hobby. And I think in a span of 5 years from now with AI technology, we could do this as a hobby if you like it. And if you want to choose this path, to study and answer some fundamental questions, for example, what was paleoclimate on Mars for for example, how cold it was 3.5 billion years ago on
Yeah.
Mars, or what was the astrobiology of things. You could study this if you want, and don't think that back into the first question, like why Earth or Mars? No, you don't need to choose. You could do different things. You could apply a remote sensing to anything. Right now, you could study Mars, and tomorrow Moon, and day after that it could be Earth or other different worlds.
Thank you very much, Rina. I hope like every students are truly enjoying today's lecture, and also like I believe like this technology and what you have been just show you will be really important to these students because of in the future they are going to learn about the fossils and the paleontology and these type of remote sensing technology, and they have some fundamental idea then even to understanding like some fossil sites they can preliminary use those things, and even for they are interested in the Mars will be upgrading. And I notice Arunan and Tevmini have been just already passing your greeting. Thank you. That's it. And dear students, from today, I am going to wind up these sessions. If you have any further more question, make sure to send us to our WhatsApp group. And if you have any further questions to the Rina, and even though it's okay, like just pass me the text and I can just share in with the Rina. And again, Rina, thank you very much for your time
Thank
and the
you.
devotion. Yeah, I know that you have been just already traveling to the Vietnam at the time, and highly appreciate to the talking to the Sri Lankan students, and that will be really motivate for the our next generations in the Sri Lanka. And we hope to see you in the future. Dear students, good night and Arena, and it's a good evening and a good morning and everything. And see you at the next week. Okay, bye.
Bye.